Hey guys, I will be explaining solutions of the Starters 44 Div 4 competition yesterday. So after the competition, I just directly slept, and because it's like midnight that time, so I just slept and didn't bother like analyzing the contest. But then okay, now I'm awake. I will be explaining my solutions for Starters 45. So it was my first time solving all problems in a competition. I think I've never done that. I came close to that in like a Div 4 round in Code Forces when I solved like 7 or something in Div 4. But yeah. So technically, I just have to admit, technically in CodeChef, like in the Div 4 rounds, two of the problems are like free or you're expected to get them. I don't see why you should not get them. um, at least two problems are free, or at least one actually. One is like literally an introductory to competitive programming, so like how you want to submit or how you want to read the problem, and so it's already given. So technically, I just solved like I don't know six actual problems or seven, depending on the difficulty of the second problem, but like the second easiest problem. But yeah, it was my first time solving all problems, and I didn't shy away from the harder ones. And fortunately, that gave me rank 30 out of like 9,800 people that solve at least one problem. So yeah, and I am in a le- leaderboard. Um, and I like their scoring system a little bit more. It's like an IOI style, yeah, IOI style rank list, meaning there's not much penalty to there's not much penalty to failed submissions. It's just that what is your last AC and how many problems you solved, which I think is actually more logical than a lot of the I don't know like the time penalties. But it depends on what you prefer. I just prefer this type because of the fact that it doesn't hurt if you submit like wrong things. Like I don't think you should penalize people that much for submitting a wrong solution, but it's fine. I guess it's just me. All right, so yeah, that's my contest analysis of my performance, and I think this was my best performance in terms of like relative ranking. Or the problems were, for me at least, like I think they were perfect for me because it's more mathematics than actual programming, which I don't want to happen because obviously I want to improve my skills in in actual like exclusive to programming, like it's not exclusive to programming, but like things that you can only really learn in when you're doing programming, like I don't know, like graph theory algorithms, dynamic programming, and stuff like that. But it's fine. This is a Div 4 round, and its purpose is to like make people improve their problem solving skills first before moving on to more advanced topics like graph theory, dynamic programming, data structures, and so on. So, and this doesn't actually like utilize any of those advanced DSA. It's just literally improving your problem solving skills and your mathematics skills. So enough of that. Let's go to the problems. So I prepared my contest submissions from A to H, and the problems weren't in order because CodeChef basically just orders them in like the number of successful submissions, and I don't know. They probably prepare it first in order of like what how they think um, the order of the problems based on difficulty should be, but then overall it will be sorted based on successful submissions um, in the editorial and stuff like that. And like, yeah, and I think that's also one thing that I like about this website is that it makes you want to solve problems because it focuses on the amount of people that solved instead of like the order of the problems. In Code Forces, you kind of like have this psychology where, oh, E is actually harder than D, so why should I spend solving E if I can't get D or something like that. So this is a pretty nice format. But anyways, let's go ahead and talk about the problems. So the first problem is best of two. So this one is what I'm talking about, like a free problem. And basically it's just gonna practice you on how to submit or what competitive programming is. So basically, you have X marks and Y marks, and you want to take the best score out of the two. So what you just do is just take the maximum between the two numbers you're given, X and Y, and that's literally just it. Taking the max of X and Y. And yeah, not much elaboration is needed. That's too basic. Okay, next problem. I don't know which one is the next problem. Okay, this one. So change row and column both. So basically, to summarize the problem, you're given a 10 by 10 grid, and then you're given uh, one coordinate and another coordinate. So you want to find the minimum number of moves to get from the first coordinate to the second coordinate, so the starting coordinate and the ending coordinate. And your moves is restricted. So basically, you can only go to another cell such that um, their x coordinates are not equal and their y coordinates are not equal. So this is the rigorous definition, and you want to find like how many moves or the minimum number of moves to go from the starting coordinate to the ending coordinate. So how do we solve that? Well, they're just I think they're just two cases for this problem. The first thing is that if these two coordinates satisfy this thing, right? So if that's the case, then you can just directly jump from the starting coordinate to the ending coordinate. Okay. So an example for that is if the starting coordinate is 1 2 and the ending coordinate is 9 8, so you can just directly jump. So it will be one move. And another case is okay if this is 8 6 and 6 8, so uh, it will be one. And then the other case is if it occurs that a is or the x coordinate is equal or the y coordinate is equal. So it doesn't matter if both are equal or just one of the coordinates, or the pairs of coordinates are equal. That means it doesn't satisfy this condition, which means that you cannot directly jump from the starting cell to the ending cell. So how do you solve that? I claim that the at most you will need two number of moves. Why is that? Because we have a 10 by 10 grid, meaning you can always pick another cell that doesn't share the same something like row and column. So you can convince yourself that that's the case, and I think it's quite easy to prove that. So meaning if their x coordinates are equal or their y coordinates are equal, then you can always do two moves because you can always pick an arbitrary cell that doesn't share any row or column with the other two cells, and then jump to the ending cell afterwards. So just like this. So in order for us to implement that, we just check if their x coordinates are equal or their y coordinates are equal. Then if one of these are satisfied, then we print 2. Otherwise, you can just directly jump, so we can print 1. Okay, that's problem 2 based on successful submissions. So I don't know which one, Chef and his apps. Okay, so this one is the second problem I solved. Okay, so the summary of the problem is that you're given a storage of S megabytes, and you're given two apps that is already installed in your phone, which occupy X megabytes and Y megabytes respectively. So you want to put another app which is Z megabytes, and it's your priority app. So meaning you want to install it. Install it. Uh, you want to force yourself to install it. Meaning, if you cannot fit it in the storage with together with the other two apps, then you have to delete some apps. So how do we solve this problem? First of all, we have to take note that z is less than or equal to s. So it's a possibility that if the three cannot really fit, or like two cannot fit, two apps cannot fit, meaning we can just like remove, we can always remove two apps and then fit z. So at most the answer will be two. Now, this is just simple. If you can fit three of them, then if you can fit three of them, meaning x plus y plus z is less than or equal to s, then you don't really have to remove any apps, so you print out 0. Otherwise, otherwise you can fit two apps because we already checked this. So if it doesn't satisfy, then automatically it's two apps or one app. So um, yeah. So you want to check if x plus z is less than or equal to s, or y plus z is less than or equal to s. It doesn't matter even if x and y are not equal. As long as it satisfies at least one, we can just remove one app, and so we will print out one. And otherwise, we cannot really fit z together with another app, so just print out two. So you will remove x. You will remove the app with x megabytes and the app with y megabytes. So that's problem letter B. Okay, so far those three problems are really easy. I think it's just logic, I guess. Like these three problems are just logic, and it doesn't really require that much mathematics yet. So this one is just introduction to competitive programming. This one is just logic, I guess, and then like an ad hoc logic, and then this one is Chef and his apps. It might be like case bash. It's kind of mathematics as well, but like it's also just logic. Okay, so let's go to the fourth problem based on successful submissions. So Jason's sum parity. Okay, so I guess this one is the first problem that requires like some thinking. Not to be arrogant about that, but like honestly, this one was the start of the competition. If you can solve this, then you will already um, you will already have a high um, like you'll already get higher rank, at least like get a lot of people will not be able to solve this if they just start out something like that. So let's summarize the problem. Basically, you're given an array B of length n, and you want to find the array A of length n, and you want to determine if you can create array A of length n. So what is B? Well, the terms in B, the ith term in B, is just AI plus AI plus 1 modulo 2. So percent 2 is the remainder when x is divided by, or x modulo y is just the remainder obtained when x is divided by y. So if you don't know that, feel free to search about modulo or modular arithmetic, and you'll get you'll understand. So this is just for the first n minus 1 terms. And for the last term, it will be an plus a1 modulo 2. Okay, so alright. So how do we approach this? First, I will claim something, and that if the number of ones appeared is even, then the answer is yes, otherwise it's no. So we have to prove that claim. So let's use this one note. Okay, so I claim that the number, so if the number of ones is even, then the answer is yes, otherwise the answer is no. So let's prove this real quick. Okay, so the first thing is that we have to review about parities and sums. So if let's say this one is any even and O is any odd. So if E plus O, then this will be odd. If O plus E, so by commutativity is just that. If O plus O is always even, if they have the same parity, it's gonna be even. Okay, so just review. And okay, so now if we're given BI, right? BI is equal to AI plus AI plus 1. So let's say we're given B1, so A1 plus A2. What if we fix A1? So this is the question. If we fix A1, we will actually determine the other numbers from AI from the other numbers. Yeah, just the other numbers. Okay. Based on the first condition. So the first condition is this one. So why is that? So let's say our first number is 1 and then 0. So they're just like 4 cases here. So the first case is like 00 and then 01 and then 10 and then 11. If we determine 00 and say this is 1, we can just break it down to 00 and 01. So we can just analyze it per pair of adjacent elements. Okay, so if it's even, then suppose suppose A1 is even. Okay, so it's any even number. So what happens is that A2 is equal to even, because if you sum them up, they must be even. So they must be the same parity. Okay, and then since B2 is even, then it turns out A3 is even also. Okay, so you determine that. Now if A1 is odd, then A2 would be odd and A3 would also be odd. Okay, and then what if here A1 is even, then A2 must be even and A3 must be odd. So if A1 is odd, A2 is odd and A3 is even. And by symmetry, you can also determine like what happens here and what happens here. So the important observation here is that you will determine the next numbers. Okay, so from here, what does it mean if we have a 1 in B? It just means that the parity. So let's say, what does it mean if BI equals 1 for 1 less than or equal to I less than or equal to n minus 1. It just means that the parity of AI will be different from AI plus 1. So we are just adding another number that has a different parity than the previous number, or the latest number, or the rightmost number. If we have 0, bi equals 0, first of all, let's iterate from iterate iterate from left to right. So if we have I is equal to 0 for 1 is equal to I less than n minus 1, this just means that we add another number at the end that has the same parity as the rightmost number in A. Okay? Meaning, if we have odd ones, then the last number will have a different parity from A1. So the last number, or then AN, will have different parity from A1. If we have even ones, then AN will have the same parity with A1. Now, AN plus A1% 2 is equal to BN, right? Okay, so yeah. Okay, yeah. So if BN is 0, then AN and A1 must have the same parity, right? So the number of ones is even. Okay. Right. Yeah. Now if BN is 1, yeah, if BN is 1, then okay, the number of ones is even for among B1, B2, up to Bn minus 1. If Bn is equal to 1, guys, then that means that An and A1 have different parity, meaning there are there are odd number of ones among B1, B2 up to Bn minus 1. Meaning, in both cases, the number of total ones is even. So that's basically the proof for this problem. Wait. Okay. Yeah, if we have odd ones among B1 up to Bn minus 1, even ones among B1 up to Bn minus 1. So hopefully you understand what the solution is. Basically, if the number in B is 1, we're just changing the parity of the latest number that we have in A. So we just have to be careful with this. So the second condition gives us the problem, or like it allows us to solve the problem and determine whether A is obtainable and or not. So this means that this second test case would not work, and this third test case would also not. So, but that is basically the fourth problem, and you can totally just guess this one actually, but obviously we'll want to prove it. Okay. All right. So now let's have the next problem, and it's the fifth problem. So this one is a math problem. So both problems that require some thinking are math problems. So okay, so let's figure this out. Okay, so let's summarize. Let's summarize the problem here. Um, okay, so let's summarize the problem. So basically, you're given a function fi, which denotes the sum of the first I numbers, and ji is the last I numbers, or last uh, what is it? Whatever. It's gi is ai plus 1 plus up to an. Okay, and bi is basically their sum for I equals 1 up to n. And you're just given b, so you want to determine a. And in fact, the constraint says that a always exists, so we always assume that whatever needed, whatever condition that you need to get a, you will always get a, so the conditions will always apply. And I will explain that later. Elaborate that later. So let's first determine what bi will be. So bi is fi plus gi, right? Which is a1 plus dot 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 plus ai, and then we're gonna add ai plus dot 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 plus a n. And this is just ai plus, or a1 plus dot 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 plus an plus another ai. And let's say that sum a is a1 plus a2 plus dot 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 plus an, and sum b is b1 plus b2 plus dot 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 plus en. And this will be sum a plus ai for 1 less than or equal to I less than or equal to n. Okay, so this means that b1 is just sum a plus a1, b2 is equal to sum a plus a2 up to bn, which is just sum a plus an. Okay, so now what will sum b be equal to? So if we add all of these, right, this will just be sum b will be there will be n of these terms, so it will be n times sum a plus a1 plus a2 plus dot 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 plus an, which is just n times sum a plus sum a, which is, if you factor, it's just n plus 1 times sum a. So sum a is actually just sum b divided by n plus 1. Okay. So how do we retrieve the array a, right? It looks like we can already retrieve a, because a1 is just b1 minus sum a. a2 is just b2 minus sum a, and so on. Right? So what we're already given what the b terms are, and we want to determine the sum a, and we already have a way to determine that. It's basically just the sum of all the b terms and dividing it by n plus 1. And what I mean about if the importance of that, the fact that you can always get an array A, the reason why I elaborated on that is because this means that sum b will always be divisible by n plus 1. So it's like an if and only if condition, I think. Is it an if and only? Yeah, it's like, since a always exists, then everything here must be true. That means we can just take each term in b and just subtract it by sum a, which is just sum b over n plus 1. So in general, bi is or ai is bi minus sum b over n plus 1. And all of these you can determine. So how do we code that? This is pretty simple. Just do whatever you proved, and you just determine what sum a is. This is that. You take the sum of all terms in b, and then you divide it by n plus 1, so you get sum a, and just subtract it to each term in b. You'll get ai. Okay, so that is the first 5 problems, and okay, so let's go for harder problems. So the next problem is called even equal odd, and to summarize, you're basically given an array with 2n integers, and you have 2 operations. You can divide an even number by 2 until it becomes odd, or you can multiply something by 2. And your goal is to make the number of even elements and the number of odd elements in the array equal. So let's determine how do we approach this problem. Okay, so the idea is that um, we split the problem into 3 cases. So the first case is that, okay, so let's first define this. So O will be the number of odd numbers. So initially it will be whatever, and the number of even numbers. So initially it will be whatever the number of odd numbers in the array, and number of even numbers in the array. So if O is equal to E, then we don't have to do anything, right? Now we will have the other 2 cases. So what about if O is greater than E? Okay, so there are 2 times n integers, and we want O to be n and E to be n. So this can change. This is a variable that can change. In maths you can't really do this, but since we're in computers, we can say that we can modify variables basically. And we want O to be n and E to be n, right? Because we want them to be equal. Meaning, if O is greater than E, then we want to convert O minus n we want to convert O minus n numbers, odd numbers to be even. Yeah. So the minimum number of operations will be O minus n, because we can just multiply O minus n odd numbers by 2. Okay, so I think this is pretty simple. You can convince yourself that everything that I just said in the previous 1 minute is true. So basically you want to make the odd numbers to be even numbers, because the number of odd numbers initially is more than number of even numbers initially. So these two cases are easy, and in fact you can really just combine this. So if O is equal to E, then it just means that O is already equal to n. So you multiply 0 odd numbers by 2. So you can just combine this if you want. Now what if E is greater than O? So again, we want O to be n and E to be n. So we must convert E minus n even numbers to be odd. But if, say, 2 to the k for k greater than 1 is divisible or divides a number ai that we want to convert to odd, then we need k operations on that number. So we divide ai by 2 k times. Yeah, so if that makes sense. This means that the optimal way is to determine the first E minus n even numbers that take the least number of operations, which is the least power k, the least power case. Yeah. So let's give an example. So let's say we have 6, 8, and 12. So say you want to pick 2 numbers, right? So obviously you want to pick 6 and 10 first, because 6 is equal to 2 times 3, and 10 equals 2 times 5. While 8 equals 2 cubed, and 12 equals 2 squared times 3. So this will take 3 operations just to convert one number, and you need 2 operations here to convert one number to odd, to become odd. So we don't want to pick these 2. So this is just one example. If you want to pick 3 numbers, then you will pick, say, 12, right? Okay, so how do we solve this? Well, we store the case for each even ai in, let's say, Bn or Be, and then we sort this array in array B. Then sum the first E minus n case, and that's your answer. So hopefully that makes sense. So basically for this case, again, let's do an example. So what about if it's 6, 8, 10, and 12? So this one will be evens, right? So evens 4. This is the array evens 4. And so B4 would be 1, 3, 1, and 2. If we sort B4, then we have B4 equals 1, 1, 2, and 3. So we take the first E minus N case. And case is the largest exponent such that 2 to the k divides AI. And how do we implement that? So you take the exponent, which is just the number of times you can divide the number by 2, which will give us the exponent. So if they are equal, then we just return this. Actually, we can just omit this because this will go to here. So if the number of evens is greater than the number of odds, then we store the case in BE. So it will be the exponent for each even. And we sort it. And we sum the first. So I did here E minus O over 2. It doesn't matter. You can also do E minus N. And you'll find that those values are the same. You can also do O minus N. And it doesn't matter. So you pick first E minus N numbers. And you sum it up in the answer variable called ANS or ANS. And we print that. Otherwise, it means that O is greater than or equal to E. So we just pick O minus N odd numbers and multiply them by 2. And that's it. Okay, so that is the 6th problem. Now let's go to the harder problem. So these problems are. So I don't expect people to get this already, or like it's gonna take quite a while for beginners to understand what we're doing here. Okay, so to summarize, you're given numbers A and B, and they will be less than a certain number. Their number of bits will be less than a certain number, and that's n. And you will find an integer x that also has the same condition, such that A XOR x times B XOR x is maximized. So if you don't know what XOR is, basically, let's say 1 XOR 0 is 1, 0 XOR 1 is equal to 1, and 0 XOR 0 is equal to 0, and 1 XOR 1 is equal to 1. Or, wait, this is 0. So it's kind of like OR, but you change this to be 0. Okay. Alright, so I'm actually wondering if we can change this problem into another bitwise operation, maybe OR, but I don't know. Okay, so let's determine how do we solve this problem. So the key idea here is how do we maximize this? Because okay, let's say you know what XOR is or what the properties of A and B and X are, but how do we maximize this? Okay. So the first thing is that how do we maximize A XOR X? Let's do this. A XOR X times B XOR X. So the first thing that we want to do is that we want A XOR X and B XOR X as large as possible, right? So we want to make them as large as possible, so that they're their product will be also as large as possible. But what up? So yeah, okay. And this means that we have some limit for A XOR X and B XOR X. Okay. Okay. Meaning A XOR X plus B XOR X must be maximized first, right? So if we want to multiply something out, both of them should be maximized, and since they are at most 2 to the n, so you will definitely find some number that will be their upper bound. The sum will be their upper bound. So you just really want to make them as large as possible. Okay, so let's prove something. So I don't know if this is called lemma or whatever, but let's say we have p plus q equals r, and we want to determine the maximum p value of p times q. And let's do this is that like p, q, and r are positive integers. Okay. Right. It's not the lemma yet. So how do we solve this? So first of all, let's express p as r minus q. So we are solving how to maximize r minus q times q. And okay, so we'll do a clever trick here. So let's first do the claim. So this is basically my motivation, is that we must make them as close as possible. So e.g. 5, 5 instead of 6, 4 or 7, 3. So, right, their product is larger than 24 and 21. So we first prove this. So r minus q is something called, is like r prime, sum r prime minus q prime times r prime plus q prime. Okay, so since they're positive integers, they will be r minus q is less or equal to q. Actually, you don't know that. But this is the general idea. Is that you can always actually we use another variable. We can always express it something like this. So an example for this is like, let's say we have 6 and 6 times 4 is just 5 minus 1 times 5 minus 1, or 7, 3 is just 5 minus, wait, this is plus 1. It's just 5 plus 2 times 5 minus 2. So we can always like express it in terms of this. Yeah. So this becomes c squared minus d squared. To maximize, we take d equals 0, meaning r minus q equals q, which is the same as saying p is equal to q. So that's the proof. So we want to make p and q to be equal, meaning actually this is not good. So we take the least p, meaning r minus q or the absolute value of p minus q is as small as possible, right? Because q minus p is just 2D, so if that makes sense. So you want to be as close as possible, and you don't even need to prove this. It's quite intuitive already and quite trivial. So we want to make a XOR x and b XOR x to be as close as possible. So let's do that. So because we want, actually let's do, wait, this should be maximized. Maximized. How do we maximize? So, okay, let's say a bit or a digit in A. So let's convert A to binary. A and B. A, B, X as binary. So let's say in a digit, let's say in a digit of A, or the ith digit of A and B, we have 4 cases. So this is the cases here. Ith digit Ti, say Ti. So if Di is equal to so let's say Ai is equal to 1 and Bi is equal to 0 or 1, then since we want x or A XOR x and B XOR x to be as large as possible, then xi is 0 to make A. Let's actually make this C, okay, and D, to make Ci equal to 1 and Di equal to 1, right? So we can simultaneously make them 1. Now if Ai is equal to 0 and Bi is equal to 1 or 0, then similarly we can just make xi to be 1 to make ci equal to 1 and di equal to 1. So to make c and d as large as possible. Okay, wait, we actually might confuse this thing here. So let's just take a note that c, d here are not the same as c and d. Okay, so I could have explained that a little bit better. Okay. So these are the first conditions to maximize A XOR x and B XOR x. So now what if AI equals 1 and BI equals 0? Or like, what if AI and BI differ? So to make since the number of since Ci and Di whenever AI equals BI is 1. Oh, not since. Okay, so this is our first observation. But what if AI is different from BI? So first, let's give you an example for this. So what if A is equal to, I'm just going to do some random binary number, and B is equal to some number here. Okay. So what will X be? And what will C be? And D will be. Okay, so let's figure things out. So this digit is the same. So we make this 1, which makes these two numbers 1. Yeah. Okay. Again, these numbers are the same. So this will be 0 to make C 1 and 1. So we want to maximize them, right? Okay, so next is this case. So we make this 1 to make this 1 and this 1. And then this 1 should be 1 and 1. And this one should be 0 to make this 1 and 1. And this to be 0 and this 1 and 1. And this one will be 1, 0, and this one will just be 1, 1, 1. Okay. So I didn't answer the instances when they're not the same. So what if AI and BI differ? So our goal is to make A and B as close as possible. To do that, but since we can only like we can only make the digits differ, binary digits differ, and 2 to the k is greater than 2 to the k minus 1 plus 2 to the k minus 2 plus dot 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 plus 1. So it's always that case. So for instance, this is always greater than this. Let's reduce the so that we don't have difficulties of like alignment. So this is always true, right? This is always true. This is in binary. So this is always true. Meaning, since actually to review here, right? If they differ, only one of them. If it's 1, if their XOR is 1, only one of them will be 1 and only one of them will be 0, right? So if they differ here and you put, let's say you put 1 in X, then AX or X, which is C, will be 0 and this will be 1. If you put 1 here or 0 here, then C will have 1 and D will have 0. So they will always differ. And this is the best way we can make them as close as possible. Meaning, we pick, without loss of generality, the first instance where AI and BI differ from the left. We make CI equal to 1 and DI equal to 0. The rest of the instances, we make DI to be 1. Okay? So the best visual is with an example. So let's use an example here. So we use without loss of generality. We can make a BI We can make di equal to 1 and ci equal to 0, and here vice versa. That's why I put without loss of generality. So we can pick A. And how do we do that? So we want this to be 1 first, so let's do 1. And how do we do that? We put 0. Okay? And then the rest, this one should be 1. So we want to make these 1s and these to be 0. So how do we do that? Well, this one should be 0. This one should be 1. This one should be 0. And this one should be 0. And this one should be 1. And this one should be 0. To make this to be 0, 0. And this to be 1, 1. So this is the closest possible scenario. You can always interchange it. So you can make this like 0, 1, 1 like this if you choose to do so. You can always interchange them and it doesn't matter. So in fact there are exactly two possible answers for x, I think. Yeah, there are two possible answers for x. But you can only print out one, so yeah. So let's worry about implementation, and the implementation is quite simple. But what I did was less mathematical, more so visual. So I just made it a string so that I can visualize it more, so that I can like iterate over digits. And the first case is that the instances of the instances are the same. So the bits are the same in a digit. So if it's 0, 0, we want to greedily add 2 to the um, 2 to the n minus I minus 1. So meaning we're adding, because x is in decimal, so we can just do this. But you can also like make another string sx if you want, but this is easier. Okay. And then if both of them are 1, then we just put 0. And this, you can even omit this if you want. Okay, now let's do the first instance where they differ. So we want to side with A. So we want to make C, which is AX or AX, to have the first instance where they differ to be 1. Right? And okay, yeah. And then the rest will be the rest where their digits differ, we will side with B, meaning we want to make B XOR X in those digits to be 1. And we print out X. So we don't have to add these, but yeah. So proof that this works, let's print it out. And we get 130, which is exactly the answer. Okay, we have our final problem. And it's called KGB and GN-Theory. So I think this one is a very funny problem because of the fact that the name sort of gave away what the intended solution is. It is basically not to use graph theory and use number theory. The only graph theory concepts that you need here is what are edges and what are vertices, and that's it. and what are undirected weighted edges. And you don't really need graph algorithms here because the number of edges will be very large. It's actually O of n squared. So, okay, so let's determine how do we do this. So in summary, basically, we have an undirected graph of n vertices from 1 to n. And if u divides v, so if if u divides v, then vertex u is gonna be connected with vertex v with an undirected weight edge of v weighted edge with weight v over u. So an example here, you have an example here. So how do we do this problem? So the idea is that we first look at the time constraints. Like this is pretty large and is pretty large. So if we actually like connect vertices based on the condition, there's so many actual like connections. There's so many connections. And how do you know that? Well, if you want to connect it with 1, because 1 divides all numbers, then there will already be like n minus 1 connections. And that doesn't count the other connections that you can do with 2, um, with 3, and so on and so forth. So it's going to be very large. And usually graph algorithms have like n v plus e algorithm to do. Like Dijkstra has, I don't know about Dijkstra though, maybe some logarithmic, and it's gonna take so much time. So you don't want to construct this graph. Okay, so how do we solve this then? The first thing that I did was I tried this sample, and it already gave me the answer. It's just that implementation quite sucks. But okay, let's first determine. It will be a very visual, so I will use pen instead of this. Okay, actually, you know what? Let's do it. So okay, um, right. So suppose we have vertices u and v such that v divides u. And suppose we want to go from u to v. So what is the minimum path? Okay, I forgot that um, you will be determining like the shortest path from u to v, considering the weights. Suppose we want to go from u to v. Okay, so how do we do this? Well, you can already like say, okay, what if we just go to directly to u to v, like the connection to u to v. This is not the optimal way because of the fact that you can always go to some intermediate nodes before. And why is this so? We have to realize that for primes p and q, pq is always greater than or equal to p plus q, and equality holds if p q are 2. For primes p greater, or we can generalize for p q greater than 1, right? Because if it's 1, then a counterexample would be 1 times 6. You'll have 7, so the sum will be 7 and their product will be 6, so obviously that doesn't satisfy. So generalize for p q greater than 1, but then all primes are satisfy this, so this is always true. Meaning, if we go, if suppose we express u to be like p1 raised to e1 times p2 raised to e2 and so on. like V is some P's and some I's, right? P I1 raised to E I1, and this is the prime factorization of U and V, by the way. And up to whatever P I, say like M raised to E I M. So notice that we can first go um, to U divided by PK. Um, yeah. Then we can go to U divided by PK squared, right? So the weight here would be PK squared. The weight here would be PK, and so on until we go to P. We go to Q. Yeah, and so this basically finishes our observation. We abuse the fact that if we decompose the path into like prime divisors of U that are like greater and that such that Q V divides those, right? We will always guarantee an optimal path, because when we sum factors, it's better than taking the whole product, right? So we just keep on decomposing them. So I'll give you an example so that you can understand later. But this is just the formal way of explaining it, so I just want to do the formal way first. So we already know how to go to U from U to V optimally if V divides U. But now, generally, how to get from U to V. So the first case is that V divides U, and we already know how to do that above. But what if V does not divide U? Then we find a vertex that they share. And what would that vertex be? Right? What would that vertex be? And optimally, you can find that this is the GCD. You can actually, you can as an exercise you can prove this. You can also choose the LCM, but since there is a limit to the vertices, you don't guarantee that the LCM exists. So choose their GCD. So why would the GCD be the optimal node, right? So basically the idea is that U only really goes to numbers that divides it. Similarly to V. Right? So suppose they share some divisor. then you will always like you will always visit the GCD based on our optimal path, right? Because we will always go to U over PK, U over PK squared until Q, right? So you will always visit the GCD, nonetheless. Right? So it will be the GCD. Because it just hurts when you pick another number because you're just gonna add the weight, right? A number that is less than their GCD, right? So it's their GCD. Now we want to know what the overall weight is. So let's do that. Okay, so notice that we're doing this, right? We can just take the path from U to 1 and V to 1 and subtract the weights of the path from G to 1 and G to 1. Right? And G is equal to GCD of U and V. So this is the case if V does not divide U. Okay. So we take their GCD and we take their optimal path from U to G and V to G. And since this is an undirected path, we can like go to U to V, right? So that's nice. Actually, we have one more thing that we should define here. So without loss of generality, let U be greater. So if V is greater than U, then just swap them. It's easy implementation. Okay. So yeah. And the sum of the path from say U to G is just okay, actually let's define it here. So the path from U to V, if V divides U, is just sum of divisors prime factors of U minus sum of prime factors of V. Right? Because we can just go from U to 1 and then go back to 1 to V. So we just take out the path going from V to 1, right? And it will be because we're like just constantly dividing these things, meaning this will have a weight of PK squared, and so on and so forth. This is not distinct, by the way. It's actually like a multi-set. So meaning if you have something like if your prime divisors are like 2, 2, 2, 7, 13, then you will add 2 again and 2 again and 2 again. but it's not the distinct prime, the sum of distinct prime factors. It's just the sum of the prime factors individually. Okay, and that's it. So here the answer will be sum of prime factors of u minus sum of prime factors of g plus sum of prime factors of v minus sum of prime factors of g. And that's it. So the key idea here is that you want to break down this problem first. Like, what is the optimal path from a vertex u to v if v divides u? And then in general, if that doesn't happen, then you can always pick their GCD, and their GCD always divides a number, right? The number. So G always divides U and G always divides V. So you take the optimal path from U to G and the optimal path from V to G, and we sum their weights. And that's basically it. So how do we implement H? So I created this very fast sum of prime factors. You can also, like, I don't know why I did this though. Yeah, I don't know why I did that, but you can start from 2 here, where like I times I is like less than n, and start from 2, something like this. But this is faster, it doesn't matter. I don't know why this is I plus 2, but it works. Yeah, this is I plus equals 2 because we want the prime factor is greater than 2, and those will be 3, 5, 7, and so on and so forth. So yeah. So that's it. And the implementation is, if v is greater than u, then we swap u and v. And if v divides u, then we just directly go from u to v. Otherwise, we take their GCD and we go from u to g, then g to v, which is just the same as v to g. So in general, here, if they don't divide each other, so you go from, the start will be from u, then you go to u, then you go to g, then you go to v. So sum of weights is just equal to sum of weights of u to g plus sum of weights from v to g. And that's about it. So I'm hoping that I explained the solutions rigorously, and hopefully it's clear as well. But if it's not, I guess I admit that the last two problems were hard to explain, so I might be at fault here, but at least the first 6 problems I think I explained, like, with ease, because the problems were easy. But yeah, that's about it, and I did really well in this competition, I think, because I solved all problems, and I also finished quite early, like 2 hours and 19 minutes, so I had like still like 40 minutes to talk about things, which is nice. But yeah, that's it, and I'm hoping I can do more performances like this. And currently I'm still in Division 4, but it's my second competition, so it's pretty nice. And hopefully by the next competition I get to Division 3. If not, then let's do more work. But that's it. Hope you guys enjoyed.